Okay, hello everyone, welcome to today's Platon webinar. I'm Zimo Yang, a second-year graduate student in Professor Wei Xiong's group at UCSD, and I will be the host of today's talk. Before we start, I will make a few announcements about future schedule and mechanisms of this webinar series. First, the Journal of Chemical Physics will have this special issue of Platon chemistry, molecules in cavity and plasmonic media. The editor will be Professor Jason, Shigai, Wei, and Hoel, and you are all welcome to contribute. The submission deadline will be October 16th this year. Our webinar will be held every Wednesday at 9 a.m. Pacific Standard Time, and the registration for each webinar can be made through this link. Here is the future schedule of our talks. Here are more details about following postdoc spotlight. We will choose 2 applicants as speakers from all applications we received based on vote, and each of them would have a 25-minute talk. The vote link has been sent out through social media, and we thank all people who have submitted this application. Another thing I would like to mention is that we created this webinar chemistry online community webpage on Facebook, which allows everyone to share papers and post announcements. You can search by its name. Meanwhile, we have uploaded our recorded videos on this Platon chemistry webinar YouTube channels. For those who missed the talk, you can subscribe and watch these videos later. Finally, I would like to introduce the mechanisms of this webinar. During the talk, attendees are all muted. For those who have questions, you can click this raise hand button, and I will interrupt the speaker at an appropriate time and enable your audio to ask questions. Also, you can type in your comments or ideas using chat function so that you can share with everyone. For Q&A, you can type your questions there, which will be addressed at the end of the talk. For questions that are not answered due to the limited time, we will collect and send to speakers after talk. Now let's move back to today's webinar. Today's speaker is Professor Javier Aspra from Spanish Council for Scientific Research at the Center for Materials Physics in San Sebastian, where he leads the Theory for Nanophotonics group devoted to the study of interaction of light and nanostructured materials. Professor Javier achieved his PhD at the University of Basque Country on the theory of plasma excitation by fast electron beams in 1998. After research positions at Chalmers University of Technology and the NIST, he worked at the Nostia International Physics Center as a physics research fellow. He obtained a permanent position as a CSIC researcher in 2008, and since then, he has been leading his group at CFM. In 2015, he obtained his position as a CSIC research professor, and from 2015 to 2019, he was appointed director of the CFM in San Sebastian. Professor Javier has studied the excitation of localized surface plasma in metallic particles induced by a variety of external probes, including light. He has developed a theory to understand the role of light and matter in a variety of spectroscopy and microscopy configuration, such as in surface-enhanced Raman scattering, surface-enhanced infrared absorption, scanning transmission electron microscopy, scanning tunneling microscopy, and scattering type near-field optical microscopy. The understanding of the optical response and complex nanosystem has been the main focus of his research, particularly merging aspects of condensed matter physics, quantum chemistry, and quantum nano-optics to address different quantum dynamical aspects of light-matter interaction, and optical spectroscopy at the nanoscale. Professor Javier collaborates intensely with some of the top experimental and theory groups of nanophotonics all over the world, and he is an author of more than 200 publications in peer-reviewed international journals relating to the field of nanomaterials and nano-optics. He has given more than 200 invited talks and seminars in university and technological centers all over the world, and has participated in several international scientific projects and networks in the area of nanophotonics. Moreover, he has organized many international meetings on nanophotonics with participation of hundreds of scientists from all over the world. Now let's welcome Professor Javier Aspra. Professor, now you may share your screen.
Thank you. Thank you very much for your presentation and your invitation. It's really a pleasure to be here and participate in this webinar series. I'm honored to be here among so many nice speakers who preceded me. Let me find my screen to share because now it's gone. Here it is. Sorry for that. Now it's coming. I hope everybody can see my screen right now.
It's good now.
So as I say, I wanted to thank you and all the department for this nice invitation to join this web seminar series. And I'm going to focus today about molecular spectroscopy, right? And how we can use a special type of cavity, the plasmonic cavity, to enhance the interaction between light and matter. In a framework of theoretical efforts in the Center for Material Physics, as you said, which is a center of the Spanish Council for Scientific Research and the University of the Basque Country. I want to acknowledge the group. Many of the results I will present are due to many people, and I want to acknowledge particularly Ruben Esteban and also Thomas Newman, who is now at the University of Harvard, but was until last year an important part of some of the results I will show you today. Right? As it was mentioned in the presentation, we collaborate with many nice groups, Sanchez Portal and Ab Initio, with direct Ab Initio calculations, Nikolai Schmid, now in Macquarie University, former PhD of mine as well, and Alejandro González Tudela in correlations of Raman, and many experimental nice groups, right? Guillaume Schul and tunneling microscopist in Strasbourg, Saint Chaldon in Hefei, tunneling microscopy, Jeremy Baumberg, who gave another talk in this webinar series, and also Francisco García Vidal in Autónoma Madrid from theory. There are some of the groups that I will mention along the talk. I didn't put here Gilad Farad, but we are collaborating with Gilad as well, and that's about it. So the talk has a general framework of interaction of light and matter, like this chemistry polariton series is all about, and is about how we try to enhance this light is that we want to increase the interaction between light and matter, and we can do that by improving two of the parameters that govern light-matter interaction, right? We can try to trap light in a cavity like this Fabry-Perot, and this we describe as an effective mode volume, which tells you how much you condensate or you improve the concentration of electromagnetic energy density here. And the other parameter is the quality factor of the cavity, which tells you how much time the light spends in interaction with matter. Light going forth and back a number of times, which is what the quality factor tells you before it escapes. And by improving this quality factor, the number of times that light is trapped here in this bounce forth and back, and the effective mode volume of this trapping cavity, we enhance the interaction of that trapped light with this matter that we locate, we position in the cavity, right? And this Fabry-Perot has very nice quality factors exceeding millions of times that the light goes forth and back before it escapes. But the effective mode volumes are typically constrained by the diffraction limit, right? We are with refractive and reflective optics, and then we are diffraction limited. In order to improve a little bit the effective mode volume, people have tried to reduce this effective mode volume by going to micro resonators, right? It's still at the diffraction limit, but making smaller the effective mode volume in this kind of cavities and putting the matter in one of the antinodes of one of these whispering gallium modes, for example. The ultimate trapping of effective mode volume is this photonic crystal at the limit of diffraction, where we can put an emitter in the middle and improve this effective mode volume with still good quality factors of several 100,000 or millions. What I'm going to present today is the action of another cavity. Let's call it cavity or optical resonator, which is built not by refractive or reflective optics, but by condensed matter excitations, plasmons in a metal, collective excitations that trap light at effective mode volumes that beat diffraction thanks to these condensed matter excitations, but with the drawback of losing energy very quick, losing the photon here very quick, quality factors of 10 or so. So after 5, 10 optical cycles, the plasmonic photons here just die, either non-radiatively or radiatively. Right? But still, this plasmonic cavity is a very interesting cavity because it will allow to target minute, very small amounts of matter because of this ultra reduced effective mode volume. And today, trace light even more. Right? And what we can do with this, I hope you can hear me. It says that the international connection is unstable, but hope you're doing fine. What we try to do is to access the matter excitations, as I say, right? Excitons and vibrations, mainly, of molecules. That's what I'm going to target today. And these molecules show vibrations and can be explored with direct infrared absorption, for example, or the electronic excitations, the excitons of the molecule, or the vibrations via Raman can be also excited with visible light, right? That's the typical kind of spectroscopies, molecular spectroscopies we can do. When we do these molecular spectroscopies in bare molecules, the cross sections are really small. So we try to enhance these cross sections by putting our molecules close to these optical resonators. Right? And when you do this in a plasmonic resonator or a metallic surface, and when you target the excitons, we talk about surface-enhanced fluorescence or absorption and scattering, right, of these excitonic excitations. And when it comes to vibrations, we can talk under the action of a plasmonic resonator of surface-enhanced infrared absorption or Raman scattering, targeting the vibrations. And in all types of spectroscopies, we generically speak of surface-enhanced, even though we know that this surface action is mainly due to the surface modes of these plasmonic excitations. Right? And that's what I'm going to try to explain a little bit better today. As I say, the nice things about this particular plasmonic resonators is the tiniest small effective mode volumes that we can get. Right? And in the last years, the nice thing for theoreticians like in our group is that theoretical groups have managed to trap single molecules and few molecules in this kind of extreme plasmonic resonators. I put these two examples, which are the two canonical examples of these plasmonic cavities, right? And some of them have been treated by other speakers in these web seminars, right? For example, this bottom-up approach with wet chemistry, when we put self-assembled monolayers of molecules on top of a gold film, we put the gold nanoparticle on top of it, and we create a nano plasmonic cavity where we naturally can do a spectroscopy, right? Jeremy Baumberg talked about this. We collaborate with him intensely. But we have another approach, which is more top-down, right? So we can have the same metal substrate with even one single molecule on top, and come with a scanning probing tip, and this tip and the metal substrate form a cavity and a very nice spectroscopy. Different varieties of spectroscopy can be done in this tunneling cavity. This we do with our collaborators in Hefei, Saint Chaldon in China, and in Strasbourg, Guillaume Schul's team in France. And I will show you some results on this. In the end of the day, when a theoretical group tries to tackle these excitations and how they interact with matter in a plasmonic cavity, you need to address several issues, right? You have this complex structure made of atoms. It's not any refractive or reflective cavity anymore. It's a kind of metallic boundary where the photons come in, all these electrons of the metal act coherently, producing a collective oscillation. They produce local fields. The boundaries create an antenna field. They can decay into vibrations, into electron hole pairs. There is even a very intense effect of atomic scale morphologies. You can drive not only with local fields, but maybe also with currents by biasing the metals. And on top of this is all just happening in the cavity, but this can also mean that we put the molecule, and the molecule needs to interact with all that dynamically. The molecule is what we want to explore, to do a spectroscopy on, and it has excitons, and it has vibrations, and all these, as I say, interact dynamically in different time scales, right? This is what we want to address theoretically. And of course, we will need to do different approaches and approximations to tackle more specifically one aspect, the molecule, or another aspect, the cavity, depending on what you target, right? And this is what we try with the different theoretical tools we try to use, right? If we want to address this nanophotonics even beyond the nanoscale at this molecular single molecule level, we need to deal with condensed matter physics methods, maybe ab initio calculations to address the local fields of these cavities. But we also want to put the matter there, our molecules, and this might mean to know also a little bit about the states, the polaritonic chemistry, or just the chemistry of these states that we put there, and know how they react to light, to currents, and so on. And finally, something that we have been exploring quite a lot in the group in the last years, mainly with Ruben Esteban as well, we quantized the electromagnetic field associated to this cavity. Right? So with all this, we try to address the different spectroscopies, as I say, putting more emphasis in one aspect of the methodology or another, depending on what we want to emphasize, right? So today, in the 40 minutes that I have left, to 35, 40 minutes, I want to talk about light emission of molecules in these special cavities, and also in the vibrations and how the vibrations interact with these photons in the cavity as in optomechanics, right? And this last part I might not go very slowly, maybe more quickly, but this I will try to do in more detail. Right? So let's start with the role and the importance of this special plasmonic modes, right? Typically, people have been addressing for many years in photonics plasmonic modes by solving Maxwell equations, right? You can get very easily with nowadays with any Maxwell solver, numerical console, the near fields around a plasmonic antenna is not a big deal. We call this the single nanoantenna. This is the dipolar plasmon that everybody knows. And this we can call in different ways. I actually had a very lively debate with Bahis Sandogar. He hated that we call this nanocavity, right? Because he said, this is not a cavity. This is an open antenna which emits, and because it emits and it's open, I oppose to call it nanocavity. Right? And he had his point, but at the same time, if we depart a little bit from the classical view and we are going to quantize this optical resonator near field, and we are going to use cavity-QED methods later to quantize it, I guess we can use cavity-QED methods and call this plasmonic resonator photons cavity photons, right? But anyway, that's my personal point of view. I think we can call this a resonator mode, and then we don't call it antenna, we don't call it cavity. What is sure is that when this single particle gets close to another particle, they not only form a different bonded new plasmonic resonance, but it also forms physically a cavity, right? So this can you can properly call a cavity plasmon or a cavity photons here, because it's not only a plasmonic resonator antenna, it also physically forms a cavity. Nevertheless, for me, this single antenna would be also a plasmonic resonator and could be treated as a plasmonic cavity in the sense of trapping photons, right? Nevertheless, the important thing about this plasmonic gap is that it is very special when it comes to interacting with light, interacting with matter, the matter that we're going to put there. And I will show you this in a second. You can only see that by putting one particle close to another, the Coulomb interaction of the two dipoles interacting, just a pure Coulomb interaction, localizes even farther the near field. You can see here the near field extends on several thousands cubic nanometers. Here it gets to hundreds of cubic nanometers. And the field enhancement value is enhanced like about 10 times already here, right? From 16 to 70, right? So this cavity plasmon is very interesting to put matter there. So that's what we're going to explore. The plasmonic cavity, the physical cavity, which is a very nice photonic resonator to interact with matter. And what we did in the group in the last years is to try to dig into what happens if you zoom in more and more and more into this cavity, plasmonic cavity, right? We get to the realm of a few nanometers, we put the molecule there, and we see that the near field of the plasmon typically, for typical curvatures of metals, extends about 10 nanometers or so. And that's a typical extension of a typical gap plasmon with a separation distance of a few nanometers or so, right? But a few years ago, in the group of Zheng Xiaodong in Hefei here, they did this nice experiment where they put in this tunneling gap, which is a plasmonic cavity, plasmonic resonator, this single molecule, and they bias the tip, and they put light in. They excited matter in this cavity. They excite the plasmon resonator. They interact with the vibrations, and they collected the Raman photon stack. So they explored the vibrations. And the results are here, which are pretty amazing, right? This is already 7 years ago, but this was a real breakthrough. They were able to, by positioning the tip on the lobe or the center of the molecules, they were able to record the vibrational fingerprints of this porphyrin molecule. And by selecting a particular vibrational mode, they were able to scan the tip and obtain the optical Raman image of this single molecule with resolution below 1 nanometer, right? And now the question emerged, how can ten nanometers in lateral resolution is 10 times bigger than this, right? And when we did a simulation at that time for interpretation of these experiments, this is our simulations on the bottom row here of each vibrational mode, we realized that ad hoc, artificially, we had to assume a localization of the field of about 1 nanometer or less to reproduce this experimental result. And at that time, 7 years ago, we didn't know why this level of resolution was possible, or what was the origin of this resolution that was even beating the plasmon cavity localization of light. So here it is when we came to zoom in even more in the cavity, right? Going to the atomic scale and see that in reality, these metallic surfaces are constituted by atomistic protrusion and surfaces that can have their own particular atomic scale response to light, right? So with the help of Daniel Sanchez Portal's team and expert in Emission, we calculated the optical response of this type of atomic scale atoms, metallic atoms embedded in a plasmonic cavity, and calculated the effective mode volume associated to these kind of features, atomic scale protrusions and so on. And what we found is that for different configurations, I show you here a facet to facet or tip to facet in blue. This one on the left would be a tip to facet here as a function of separation distance of the junction of the cavity. When one gets to about 5 angstroms, below 1 nanometer, you get to effective mode volumes below 1 cubic nanometer. So somehow this is sub-nanometer effective mode volumes and localization of field, right? And that we term, not at that time, but later with Jeremy Bomber, we termed this a special effective mode volume below 1 cubic nanometer, a Pico-cavity, just simply because it goes below the cubic nanometer, right? So this is a special feature embedded in the plasmonic cavity that seems to localize even better light, and this can be very useful. To interpret this, later in the group, we did something very simple, right? This on the left, I'm showing you the near field of such a atomic scale protrusion and the field enhancement here, which is around 20 here in this atomic scale protrusion. What we did is to follow the electronic density profile in a classical interface here in the middle panel And we managed by doing so to reproduce in a classical calculation all the distribution of the near field, and even more important, the actual value of the near field. So by doing so, we can recover the quantum mechanical feature of the atomic scale by doing just a simple classical calculation following the electronic profile. This is very powerful, right? And actually, this can be understood as a very simple terms of an atomic scale lining rod effect, right? If we have a perfect metal and we have a protrusion of an ellipsoid, for example, here on the right panel, you see B semi-axis and A, and we plot the field enhancement here on the left as a function of the ellipticity of this protrusion. This is the lining rod effect. We see that over the background enhancement, we improve for large ellipticity a factor of about 3 to 4. And when you do the full quantum calculation, that's pretty much what you obtain for the classical one with the profile, with the proper profile. So somehow this atomic scale lining rod effect is concentrating light about 3 to 5 times more on top of any background plasmonic cavity field that you might have. So this is a kind of cooperative effect where the Pico-cavity enhancement is added up on the whole plasmonic field enhancement, which is already large. Okay, sometimes 4 or 5 times enhancement over a background can make the difference between detecting or not detecting a molecule or a vibration or an exciton, right? If you made the profile of this lateral resolution for different protrusions, here we start with a simple gap, plasmonic gap, where we have this blue curve. This is the lateral extension of an induced plasmon in the gap in blue. And now we artificially start protruding this feature in the gap. We see how we increase this factor of 5, sometimes 6, and more importantly, very localized in space of about 1 nanometer, the plasmonic field. So this cavity, this Pico-cavity, is a particularly good photonic cavity to interact with matter because it can give you resolution and very low effective mode volume. Let's try concepts of surface-enhanced fluorescence, right, or luminescence. We have our resonator, not Pico-cavity, now it's a generic one, a big nanoparticle. We have the exciton. Signal, right? So we want to explore this in a generic cavity to know better later what a Pico-cavity can do here, right? That's what I'm going to plan to do in the next 5 minutes. Generic plasmonic cavity, not Pico-cavity, just a general resonator. It could be even a single particle. We have the exciton, as I say here, characterized by an intrinsic spontaneous decay, gamma. We have the decay of the plasmonic or the cavity photons here, kappa, right? These are the 2 decays, the cavity decay, the plasmonic cavity decay, and the molecular excited state decay, right? And now we make them interact because we just put one on top of the other, right? And this is acting the local field of the cavity on the dipolar moment associated with this excitonic transition. And the interaction rate of these 2 entities, the field of the cavity and the dipolar moment, is just basically given by the scalar product of the dipolar moment and the local field acting on that dipolar moment. This is an energy, right? Also understood as an interaction rate, how fast the energy of one goes from one to another, how they interact, an interaction rate. And depending on this interaction rate, it's well known in this web seminar series, and this has been said several times, we can distinguish two interaction regimes. I'm going to repeat it just for those who just come to this talk. We have a weak coupling regime where this interaction rate is lower than the decay of the cavity or the decay of the exciton. Somehow the interaction rate doesn't have time to interact before the photons are gone. So this means that the energy of the optical mode and the energy of the exciton remain unchanged. They interact weakly, they can interfere, but they don't change their energy, right? This is what we call the Purcell factor, because What it has an effect is on how quickly this exciton decays. Now, because of the electric field of the optical mode, it will decay faster, but not changing the energy. Strictly speaking, there is a change in energy called the lamp shift, but which is in principle smaller than the energy of the exciton, right? The other regime is the strong coupling. You are familiar with it. Now, the interaction rate, for some reason, because the effective mode volume is small, because the quality factor is good, because it's just in the middle of a good field, this is very strong. It means that the exciton and the plasmonic field or the cavity field interact very fast before the photons are gone. So this produces a kind of hybrid solution between the optical mode and the excitonic mode, producing this lower and upper polariton that you have seen in this web series so much. In real time, if we make a spectroscopy in real time with pump and probe or something, we would follow the oscillations between these upper and lower polaritons in what is so-called the Rabi oscillation, right? This is just what I said. Pictorically, in weak coupling regime, what we have is an effect of the interaction that broadens the spectrum of emission of the exciton. And this in time means a faster decay of the exciton. In a strong coupling, in the emission spectrum, we would have a double peak of the upper and lower polariton. And in time, we would have these Rabi oscillations. Let me show you an example of this weak coupling regime in this particularly good plasmonic cavity, right? I mentioned how this tunneling cavity, the silver tip on top of a metal surface, is a particularly good plasmonic cavity. We put a zinc phthalocyanine here, the group of St. Chaldon in Cafe did, and now they position their cavity on top of the molecule in these three positions, 1, 2, and 3. In position 3, the cavity, the plasmonic cavity, is very far from the molecule. This is topography of the molecule, right? So now if we record the electroluminescence, the luminescence of this molecule in this situation with the plasmonic resonator very far from the molecule, this is the result. We have the fluorescence of the plasmonic cavity, basically. Just the electrons driving the tunneling junction, producing elastically, coupling to a plasmon, and the plasmon emits. This is direct plasmon emission from the cavity, very broad, and it's just a plasmonic resonator in this very far position. If we now put the plasmonic cavity on top of the molecule, somehow there is a quenching that produces the emergence of the exciton directly, right? You can see here in this blue position how the electrons tunneling regime where the excitation and the plasmon exciton interact. And this is the result of such an interaction, right? We have the plasmonic background and an interference, destructive interference of the exciton in kind of funnel-like profile, which produces this nice interference pattern, right? So this we can control actually by positioning farther or closer to the plasmonic antenna. When it's closer, the funnel profile emerges. When it cuts away, it's just the plasmonic feature remains. And we can do theory, just simple harmonic oscillator coupling to connect the depth of this funnel profile with the coupling strength, right? You can express the coupling strength as a function of this contrast of the funnel profile, this D funnel, and we can obtain a very good agreement to monitor the coupling, right? So this is very nice. We can control at the weak coupling limit, the coupling of an exciton and a plasmonic field almost on demand and activating or deactivating it. But here when it comes a very important question that we need to do ourselves, and many of you might know about it, particularly if you saw the webinar by Jeremy Bomber, but I don't know if everybody's familiar with this concept. Why do we see light emerging from an exciton in a plasmonic cavity when the plasmon cavity and the metal is about a few angstroms or 1 nanometer close to the metal? Why the signal from the metal, from the exciton, is not quenched by putting a metal so close to the exciton? I'm telling you, and I'm showing experiments where fluorescence from this cavity is emerging with the exciton close to a few angstroms from the metal. we all know from the paper of Lucas Novotny, which is one of the ones that brought this very clearly, right? That when you put an emitter here on the right, the one I said close to a metallic nanoparticle or a metallic surface, the emission of this emitter, in principle, can be enhanced by the interaction with the local field, but it can be also quenched if you get too close. Why? Because the emission rate of this emitter close to the antenna is composed of the product of the excitation rate, which increases as a function of separation distance monotonously here. It doesn't matter how close you go, you get farther or farther field, local field enhancement, so you get farther enhancement. But there is another factor here that we call typically quantum efficiency, right? And the quantum efficiency, which is just the radiative yield compared to the total rate of the emission, which actually starts decreasing when you get close to the surface, right? So we can see here how the quantum efficiency, how the radiative rate decreases and quenches the signal when it gets too close to the metal. This is the source of the quenching. Now the emission is the product of these two. When you make the product of these two, you get, for different sizes of the particle, this cut of the emission. This is the quenching, right? And it typically happens at about 5 to 10 nanometers from the surface of the metal. So this is what I was asking you before, right? If we get quenching in typical metallic nanoresonators and plasmonic resonators, when the emitter is close to 5, 10 nanometers, how is it possible that in a tunneling junction or in a particle on a mirror configuration, when we have separation distances of 1 nanometer or even half a nanometer, light can come out at all, right? This is another, I will answer to that in a second, after the commercials, right? This is another calculation we did now with Yao San, formerly in my group, about to come out of this kind of emission from an exciton close to this nanoparticle, and where we see the same. This is the excitation rate for different sizes of the particle. We see that it increases for short distances, but the quantum yield is killed and it's quenched when you get too close to the metal, right? So basically this corroborates the Novotny's result that if you go with an emitter very close to a metal, you basically quench the emission. Now, what happens in a plasmonic gap in a junction? What happens in a plasmonic junction is that the local density of electromagnetic states changes compared to the single particle. Here, I am plotting the excitation rate, the quantum efficiency, and the final emission rate, which is the product of these two, for these two situations, right? The open particle, where the emitter is put as a separation distance here, tip molecule distance, and the same situation. We see that whereas in an open nanoparticle, the quantum yield is quenched, right? When you get too close to the metal. It's not quenched so much until you get to very close, even at 1 nanometer or 2. And this happens just because the radiative rate of this plasmonic antenna is really good and it beats the non-radiative rate, something that doesn't happen in an open single nanoparticle. So in this sense, the metallic gap, the plasmonic gap, is a very special photonic resonator because it allows to locate an emitter close to the metal, almost sub-nanometric at a few angstroms without killing the emission rate from that emitter. So to the question of why we have light at all coming in a junction when it's so close to the metal is because the cavity gap, the plasmonic gap, has a radiative yield that beats the non-radiative. And as a consequence, this gap in red emission is enhanced even for distances as close as 1 nanometer, something that doesn't happen to the open particle. This, I invested quite a lot of time to tell you about this because it's very important. For many years, many tunneling microscopists and people in plasmonics were coming and asking why this is happening, well, why we see light at all, if we shouldn't see it. And this is the reason why. The local density of electromagnetic states, the radiative or non-radiative nature of the mode you excite or you couple to is absolutely crucial to see how you couple and how you can extract the light. For a standard nanoparticle, you wouldn't see light, even if you are close to 10 or 5 nanometers. But for a plasmonic gap, you see the light, okay? And exploiting this action, we have seen an explosion of interaction of excitons and plasmonic particles in the last years, right? I am naming here a few ones. Many of them have been talking in these web seminars. This is the work of Baumber when they put the dipole gap what allows to see light, okay? I see there is in the chat. Any question?
Yeah, I think we have two questions.
Okay.
Think Hannah, I think you can talk now.
Yeah, hi. I had a question about the plasmonic nanocavity. So why is it that the quantum efficiency is so high the moment you place a silver substrate compared to when you have an open?
Yeah. So in this situation, it's not very intuitive, right? But I'm going to tell you what. In this situation, when you have a single particle like that, the emitter is here. The mode, the plasmonic mode you couple to, in the best case, in resonance, it would be kind of a dipolar mode, right? Some kind of positive charge here, negative spread here, and it would be, this is a kind of radiative mode, but it's not so radiative, right? It's kind of charges shape and so on, but it's limited, right? When you get close to the metal, the non-radiative yield starts being larger than the radiative rate, okay? So it's just that the losses that it goes to non-radiative processes beat the radiative yield because the radiative yield of this structure is limited. It has a moderate dipole. However, when you form a gap, very radiant. It's very dipole. It's a very good emitting dipole. It's a very good antenna. You produce the charge here, positive, the charge here, negative. So this doesn't have the typical plasmonic localization of the whole particle. No, it's what I show in the beginning of the talk, right? You localize here in the gap. Now it's a gap of 1 nanometer. You produce a super dipole, super concentrated and very, very radiative.
So this is
so the radiative rate of this is so large that it beats the non-radiative rate, no matter how close you are. Finally, of course, if you get attached, you will quench. Okay, it's just that the quenching happens at very, very close to the surface. But the reason, answering to your question, is that the radiative nature of the dipole created in a gap is much more radiative than the mode of a single particle.
So this is because the gap is very small, so the dipole moment that you generate becomes very large.
Yeah. So if you have a gap of 5 nanometers, this effect is also there too. But when you produce a gap of 1 nanometer and then actually you can see this is a very good, if you put not substrate, then it's quenched. You can see it here. This black curve tells you that if you get close without the substrate, without the gap, you just kill. You need the substrate here in red to overcome this. But finally here, that's what I'm saying, if you get too close, finally it will drop, okay? At a few angstroms.
Thank you.
You're welcome. So should I continue? Let me see how I'm doing time.
There's one more question from Joel.
Yeah.
Hi, Javier. First of all, I think we are seeing the connection is a little bit rocky. So if you can switch to something, that would be great. If not, you don't worry about it. But I have a very quick question. So, I mean, the right-hand panel looks like, say, one of the Baumberg cavities. So my question is, why do you not see strong coupling and you just see the final resonance? Is it because of the orientation of the dipole of the molecule? Because the way Bamberg explains that you need the dipole to be pointing perpendicular to the substrate if you want.
Exactly,
Okay.
exactly. You ask the question and you answer yourself, right? So this structure is common to the tunneling junction or to the Bamberg particle on a mirror, right? That we have studied with Jeremy for so many years. In the tunneling junction, they don't see a strong coupling. They just see funnel, the funnel that I just showed you, because the dipole is transverse to the cavity. It's in this direction. We typically map porphyrins, which have their excitons in this direction, right? And then when you multiply, the coupling is a scalar product of the field by the dipolar moment. So this scalar product is almost zero if you put the local field like this in the cavity and the transverse dipolar moment like that. The key in Jeremy Bamberg's paper is that they managed to use a particular molecule in a curvature that they put it standing up. And because they put it standing up here, the dipole is aligned parallel to the local field, and then they get a strong coupling naturally because of that.
So have there been any experiments where they just use these tips, but then they are able to align the molecule perpendicular to the substrate?
Not in tunneling, as far as I know, because in tunneling it's very difficult. For tunneling, you need separation distances of a few angstroms, sometimes 8 angstroms or so. So there is not that much that can fill in the gap. Even the porphyrin is already a few angstroms high, right? So yeah, no, it's not easy to put a standing up molecule in a tunneling junction. But in a particle on a mirror, you do the self-assembled monolayer, you deposit the particle, and it's sandwiched directly, right? So
I see. So it's a chemical thing. Okay.
Yeah, it's a chemical thing rather than challenge than anything else, I would say.
Thank you.
Okay, here's
I need to apologize about the quality of the internet. I don't know what's wrong because I'm at university with full bandwidth and everything, but there must be some.
No worries. I mean, I think maybe if we lose you, we'll just ask you again to repeat that. But thank you.
I'm going to renormalize the content of the talk. I think I will skip the optomechanics because last week Claudio Genes talked a lot about optomechanics. I might say 2 minutes about it and not bother you more than 5-10 more minutes or something.
Professor, there's one more last questions. Randall, you can talk now.
Thank you. So in the kind of textbook definition of what you need, the ingredients that you need to get single molecule SIRS, this is typically not with Pico-cavities, with merely nano-cavities or rough surfaces. You need something like a 10 to the 8th electric field enhancement. And then you also need another factor of something like 10 to the 3rd from the so-called chemical enhancement that requires some type of hybridization between the molecular orbitals of the molecule and the surface. In the single molecule SIRS traces you're getting from these Pico-cavities, am I correct to say that there is no chemical enhancement? Because if there was chemical enhancement, then you'll be so close to the surface that even in the Pico-cavity could be quenched.
Yeah, you're right, and this is exactly how it is, right? So the fact that I'm going to bring a Pico-cavity to probe single molecule doesn't mean that there cannot be single molecule spectroscopy. Resolve the single molecule, even intramolecularly, right? But this doesn't mean that you need the Pico-cavity to do single molecule. You can do single molecule spectroscopy, as you know, putting it in a dimer and obtain the signal, right? But on the second part of your remark, you're totally right. They put on top of the metal substrate 3 layers of sodium chloride. chemical quenching. So if you put the molecule directly on top of the metal substrate, you quench everything. You don't get signal. So you're right. So these are the kind of chemical tricks of many years of development that allow to obtain signal. So it's the sum up of the detach with the 3 layers of chlorine sodium to put it in the cavity, in the plasmonic cavity, and as I show you later, the Pico-cavity to get the resolution. It's the 3 things what gave the Pico-cavity resolution of single molecule inserts.
Thank you.
Good, it's very good that we had time to do these questions. Let me just continue here with the Pico-cavity action. I want to show you the Pico-cavity in action, right? This was before for a standard gap, right? A standard gap versus a single particle. Now, I'm gonna compare the local field that we produce in these cavities, special cavities for our molecules. And I compare here the cavity without Pico-cavity, just a gap, a standard gap, and the gap with a Pico-cavity. And you can see how the perpendicular and the parallel local field at the gap, it's kind of 10 nanometers is what I showed you in the beginning for a standard cavity, plasmonic cavity. And when we put the Pico-cavity, this localization of the field gets reduced to 1 nanometer or sub-nanometer. There's more questions here, I think. No, it's thanks only, just, okay, good. So this is a tremendous effect when it comes to the excitation rate already, right? So the excitation rate is able to produce a source of localization in the 1 nanometer scale, just by putting an atomic protrusion here, right? And when you put this atomic protrusion, the quantum efficiency actually gets improved about 1 or 2 orders of magnitude with respect to not having the protrusion here in black, right? So the cavity gets very good result even at 1 nanometer, but finally gets quenched, right? The single particle would get quenched at 5 or 10 nanometers. But with the protrusion, you extend the quantum yield even a little bit more, right? So for the photoluminescence intensity, you also improve several orders of magnitude. Again, an improvement of a factor of 4, 5, 6 in this kind of localizations and field enhancement has a tremendous effect in the final intensity of the emission for 2 reasons. The actual enhancement and the fact that you are able to get the photons out, that you wouldn't be in any other way, right? The next ingredient will be just the molecule itself, right? And let me just use 5 minutes for this before I finish. Most of the emission of an emitter close to this kind of plasmonic cavities are described within the point-dipole approximation, right? So the emitter is a point-dipole, as I said, and you put this point-dipole in the local field. It can be a cavity, it can be even a single plasmonic particle, and this is the coupling rate, right? But in reality, the plasmonic field, when you picture the near field, is very inhomogeneous. The field is so localized in the nanoscale that it varies a lot along the nanoscale. So actually, when the molecule starts being of a size of the decay of the plasmonic field, the actual size, the distribution of the electronic transition associated to the exciton matters. So with Thomas Newman, who's now in Harvard, he started in our group with me trying to describe what would happen if you actually account for the whole spatial distribution of the electronic states. This is real polaritonic chemistry, right? So instead of describing the point dipole here in red on an electric field of the plasmonic field like that, what we did is to describe the whole exciton transition density, electronic transition density, and build the coupling as an integral in space and a convolution of the electronic state transition and the plasmonic potential, the plasmonic field. And when you do this, you obtain a different coupling rate, right? So in other words, what we are trying to obtain is the coupling rate within this model, the point dipole, or within to do the nice resolution with the localization here. he used this synthalocyanine of the experiments of the Chinese, and he mapped in a space the coupling strength for the point dipole and the full quantum model. And in the point dipole, you can see two differences with respect to the quantum model. First, the numbers. In the point dipole, the coupling strength is kind of too large. It's overexpressed, right? But when you spread the exciton along the space, then you get a smaller value of the coupling strength, right? And another important feature is the distribution and the structure of the coupling. Here you see isotropic distribution with a black spot here. Here in the full ab initio quantum model description, the 4 lobes of the synthalocyanine emerge in the coupling strength structure. So this really is going to allow to do intramolecular microscopy at this level, right? And the example I want to show you is the final example of the use of the Pico-cavity to address fluorescence of a phthalocyanine. In this case, a free-based. And this is done not by the Chinese group, but by Guillaume Schul in Strasbourg, another very good tunneling microscopist. He put this free-based phthalocyanine molecule in this plasmonic cavity, tunneling cavity. And the nice thing about this molecule is that it's a tautomer, right? It has these 2 hydrogens, and these 2 hydrogens can go this way or orthogonal, right? And the chemical composition is exactly the same. But the dipolar emission, most important one, is associated to the direction of these hydrogens. So if the molecule is in this direction, it will emit with a dipole like this. If it's in this other direction, the hydrogens, the dipole will emit like that. And now what Guillaume Schul's team in Strasbourg did is to record the luminescence map here on the left of these 2 tautomers, right? And they saw precisely these 2 excitonic emissions, right, in the plasmonic cavity. And one is connected with the tautomer in one direction, and the other one is connected with the tautomer in the other direction, right? They can do a spectral filtering, and they can map the dipolar emitter with sub-nanometric resolution in this direction or in the orthogonal one. You can see here QX1, this one in red, and orthogonal, the QX2. QY is the orthogonal in the other direction, which is smaller, right? But this is the 2 important ones. And they can actually filter, do the correlation on when one hits or the other one hits, and they can see that they hit in a telegram kind of fashion. So when one hits, the other one doesn't hit. So this is a clear hint of tautomerization, and they can even get the tautomer's lifetime and so on. So what we did, and with this I finish, I promise, is to put all the ingredients I mentioned until now to reproduce these experiments, which are not trivial to interpret, right? So first of all is this coupling strength, because emission is going to be proportional to the square of this coupling strength, right? So then we need to put all the ingredients I said, the Pico-cavity, the electronic exciton, and make the whole convolution here. And when you do that, what you obtain is this kind of dipolar pattern emission, right? But this is not what Guillaume's team obtained in an experiment. In the experiment, there's some kind of dipolar emission, but it's substructure here internally, right? So something else was missing here. And the point that is missing here is the pumping rate, the excitation rate, right? So in this case, the excitation rate instead of light is the electron tunneling current, right? The electron tunneling current is pumping, right, the energy to the system. This is not photoluminescence, it's electroluminescence. So we have to put here a factor, which is basically the current, the inelastic current driven through the exciton. And actually, this pumping factor, I'm going to go quick now, is Thomas saw that it was proportional to the HOMO, to the highest occupied molecular orbital of this free-base phthalocyanine. It looks like this, the HOMO looks like this. And now if we want to obtain the full emission probability as a product of the pumping probability and the emission probability, so this dipole and the orbital information, the product of both, gives you a very nice dipolar with substructure given by the atomic orbital, which is exactly what the experiment was reporting. So this experiment is really amazing because it gets fluorescence from a single molecule. It dissects the internal structure of the emission, And it shows that it's not only dipolar, but it accesses information of the orbital in some way that needs to be corrected. Now it's 1 hour. I think that probably I should start finishing. The last minute that hint that I want to give is about what can happen if you go beyond this quantum chemistry and classical description. What we have done in the group, just 2 flashes, is to quantize these plasmons in the cavity-QED fashion, just quantizing the field. And the quantization of this field goes with this plasmon exciton coupling through the standard James-Cumming Hamiltonian that has been addressed. Hamiltonian in complex exciton dynamics in these plasmonic cavities, right? So I want to call to your attention this work where we go beyond the James-Cumming Hamiltonian to address fluorescence when these emitters are coupled to reservoirs, right, of internal molecular vibrations and environmental degrees of freedom. And if you do a standard James-Cummings, then the upper and the lower polariton will follow some kind of internal decay dynamics, which is equal for upper to lower or lower to upper. And when you excite this exciton, the emission basically will show this kind of homogeneous double structure of emission. Whereas in the experiments, this is not the case. When you have the environment and coupling to the environment, typically the emission happens from the lower polariton. And what we did with Thomas Newman is to develop a model where this structure of this polaritonic structure couples to the environment, modifying the rates between upper and lower polaritons and checking that the decay from the upper to the lower prevails. And then you always have emission from the lower polariton, no matter how you excite the polaritons, right? So this is an example of making more complex the quantum dynamics of an emitter than just the simple James-Cumming Hamiltonian by coupling it to the environment. And the last thing that we are doing is something with Gilad Haran that he explained very well himself, is putting now not a molecular quantum dot on a plasmonic cavity. And instead of doing the typical James-Cumming Hamiltonian with the lower polariton and the ground state coupling to the cavity, that gives this strong coupling in the scattering, a very weird and strange photoluminescent spectra, very relatively broad nanosecond correlation, second correlation features. These require also that we sophisticated the structure of levels with the incorporation of a dark state associated to the surface states of the quantum dot. And this helped to reproduce exactly the experiments of Haran in the scattering, in the emission, and most importantly, in the correlations with a kind of double lifetime presence with one of them is not resolved. I know it's this, I said in a flash, it's just to show you 2 examples of what happens when you want to address a more complex dynamics of the excitons that goes beyond this simple weak or strong coupling within James-Cumming Hamiltonian, okay? And with this, I think I'm gonna put an end. I focus mainly on this molecular light emission in Pico-cavities with atomic resolution. And since Claudio Genus talked about optomechanics and Jeremy Baumber also talk about this, I'm gonna skip this and just let you know that we do all this that we did for excitons. We do also for vibrations in Raman spectroscopy, where we use Pico-cavities, we identify pumping regimes, nonlinear regimes of optomechanics, collective effects, and resonant Raman. And this probably can be for the next year webinar in San Diego and any other webinar, and I can be more specific about this. So with this, I think I'm gonna put an end to the Pico-cavity in action for fluorescence and in molecules, and I'm very open to any more questions if there is any.
Okay, thank you, Professor. We have a lot of questions here. Christophe, you may talk now. You should unmute yourself first.
Okay.
Okay.
Yes. Is it working?
Yeah. We can
Okay,
hear you.
excellent. Okay, yeah. Hello, Javier. So,
hello, Christophe.
I have a question regarding your the simulation of the Pico-cavity and the tip. I mean, yeah, whatever you describe as a Pico-cavity situation, what is the equations that you use to simulate? Are these simulations based on the standard Maxwell equation, and then you just make a feature that is very small, and from that you obtain these results? Because it seems that at this scale, when you are talking about single atomic protrusion, can you really assign an effective index dielectric function to these surfaces or this geometry? Can you be sure that this is holding at this scale actually, or would you require like really like DFT calculation, but on some? Or what do you do exactly? I didn't understand.
Absolutely, absolutely. I'm gonna try to put again the emphasis in my message, right? So you're right. We do this kind of calculations based on classical Maxwell equations, right? And even this improvement of quantum efficiency, we use exactly, or for example, for this one, right? To compare protrusion or non-protrusion. I do exactly the same, or we do exactly the same framework of Maxwell equations to calculate the excitation rate, the quantum efficiency, and therefore the product of both, emission rate. So your question is legitimate, right? When you are in an atomic scale protrusion, that the one I'm pointing out here, right? Atomic scale. How much can you trust this red line with protrusion compared to the black one if you are using methods that at the atomic scale here might be questionable? I mean, non-locality, dynamical screening, spill out. And in order to do this and to trust that the orders of magnitude, and this is kind of okay, is the reason why we did what I explained in the beginning. And this paper for me is very important. And it's not very important because we did it. It's very important to trust these results that you are asking me about. In this paper, we take the full quantum result at the best level that people in ab initio can do. Comes off the metal, and you see what is the field enhancement. You see what is the non-radiative thing. You see all the properties of the electromagnetic fields. And now you take a classical local description, which is what we do in this final stage that you questioned, and we reproduce with the local atomic feature profile all the features of the full quantum mechanical calculations that serves us as a guide. So now, answering you more directly, if I didn't have this quantum reference as a full calculation, I could not be sure that this is legitimate. But because we have done this comparison and it works extremely well, this classical reproduction following the profile is robust against electronic spill out, dynamical screening, non-locality, and so on. So I feel that after this check, I feel legitimate to treat fields in this way, in an approximate way. That would be my answer, my honest and truthful answer on this.
Okay, yeah. But if the molecule is very close, you would expect things to be even different.
So I would expect that if the molecule is too close and you start having charge transfer, then you need to incorporate the molecule into the ab initio calculations. Totally right. But in the tunneling up, these guys, actually the breakthrough of these guys 7 years ago was this sodium chloride bilayer that prevented the chemical. We can do all this because of that. In the particle on a mirror with a tile direct attaching, I would need to do the full quantum calculation of the bonding with the tile and then try to figure out the classical analog. That I would completely agree.
Okay, yeah. Thank you.
Hello.
Hello.
Hey, so I had a question about the Q-band spectra for the two tautomers. If you could pull that up.
Excuse me, say that again. I couldn't hear you.
Yeah, the Q bands, the two Q bands between QX and QI for the two tautomers.
Oh yeah.
That you did.
The emission of the Tautomer, right?
Yeah.
This one.
Yeah, this one. Yeah. So. Yeah, so my question is about the QY band. So I'm wondering why I would expect it would follow the same pattern as the QX band, or at least maybe one wouldn't be shown. Why is it that the Tautomer 2 has a far more emission than the first Tautomer?
Yeah, so let's say that the ground excitonic, main excitonic emission is this KX, which we call QX, along the hydrogen atoms, right? But then there is another emission which is orthogonal to it, which is from another excitonic emission, which we call QY, in the transverse direction. But it's a smaller, here's multiplied by 5, right? And you see, for example, here there's almost no resolution, it's too much noise. But here you can see it, right? It's kind of transverse to the QX. So probably that's what is confusing you. Let me, and I didn't mention it, that's important, is that the attachment of the molecule to the surface has a certain asymmetry. So the lattice orientation of the surface, it produces that the exciton in one direction on the surface and the exciton in the other direction of the surface are not completely degenerate. We have done ab initio calculations to corroborate that, and it gives the right splitting of a few millieV. And this QX1 and QX2 should be equivalent if the substrate would give an equivalent attachment. But because it's not, one is slightly more compressed than the other, angstroms or tenths of angstroms, then you have this split between QX1 and QX2 that should be degenerate. But then the other thing is the other exciton, which is another exciton, okay? Probably this clarify your.
Yeah, okay, that asymmetry.
This break of degeneracy. Yes, thank you.
All right, thanks.
Actually, this is what allows to do this filter spectroscopy. Without this break of degeneracy, we wouldn't be able to split QX1 and QX2. Yeah, that's a very important point.
Yeah, Matthew, you may talk now.
I have a question about the first part of your talk, and back to the enhancement of the quantum efficiency when you put the substrate. So yeah, you mentioned that the increase in the radiative decay compared to the non-radiative decay is much faster when you put it's much higher when you put the substrate. But I'm just curious, how much does the non-radiative decay increase when you put the substrate? Because I imagine when you have now two sources, right, of non-radiative decay, both the tip and the substrate, you could get higher, non-radiative function too, right?
Sure. I mean, obviously the non-radiative decay is there, right? I mean, you're putting an emitter close to a metal, and it's providing the ohmic losses, all this. I mean, and now you're putting another metal on the other side, so it's at least twice that, right, for that distance. so it's not that you have less non-radiative rate, but the radiative rate that the dipole, the sandwich dipole of the metal insulator metal produces is way much more than that. So even if you lose with some additional metal there, in principle might be detrimental. And one might think, well, if I put even a metal, I will get even less. This is crazy. I will not try that. You might think a priori. Well, no. I mean, actually, having the sandwich metal provides a little bit more quenching, but the radiative yield beats by so far that it's actually good. But what you are saying is right.
Cool. Thank you.
Okay, one more, another question from Marisa Richman.
Yeah, thank you. Yeah, I was thinking about the last part of your talk, moving beyond the dipole approximation. I'm wondering if there's any way to tune like the transverse nodal structure of the excited plasmon field if you wanted to couple more strongly to a specific shape of molecular orbital, if there's any prospect for that.
Yeah, this is a good idea. I mean, I guess, yeah, I would love that, right? I mean, let's take this example, right? I mean, if I understood you correctly, you suggest, well, is there any way to try to engineer or manipulate these fields in some way that we can adapt them better to the excitonic to create what we want? But that would be actually atomic scale or picophotonics engineering, if you want, right? I think we are still a little bit far from that, because these pico-cavities are generated almost randomly. Of course, in nanoparticle on a mirror, even in tunneling junctions. And very often, the guys in tunneling tips, they crash the tip and they produce one situation, it's not good, they crash again until they get the pico-cavity or protrusion, right? So now we know how to engineer nanoparticles with etches, ellipsoids, rods, this, that, but this is at the nanoscale. And even that is challenging sometimes, right? With lithography and with chemical synthesis. Now to start engineering fields at the at the subnanometric inhomogeneity level to map and adapt better with chiral excitons or with whatever, well, that would be a dream, but of course it would be nice. I don't know anybody who can manipulate local fields at the atomic scale in a control way, so to say.
Okay, sorry, now just some internet. And there's one more question from Arctic Madel. You may talk now.
Hi. I have a question about your spatial dependence of the electromagnetic field you were just showing. Yes. So when we formulate the d dot E Hamiltonian beyond this long wavelength, we should in principle get like quadruple moment or octuple moments, right? So I'm wondering whether your integral inherently captures those higher moments.
Well, there are two different orders, right? Are you referring to the plasmonic orders or to the excitonic orders?
I'm talking about the electromagnetic field spatial dependence. So,
okay.
Yeah.
So what we did, that's right. So because you have excitons which are dipolar, but you have also transitions which are dark, which are quadrupolar, right? And those actually are, you can use this kind of cavities to enhance and become these dark quadrupolar excitations bright, for example, right? I didn't mention it, but that's something you can do. But that's one thing. What you are referring to is to the different orders of the electromagnetic field. By expanding the electromagnetic field in the Pico-cavity on quasi-normal modes or similar, and Thomas Newman actually expanded the electromagnetic field in the Pico-cavity in all the modes, then we are accounting naturally from all these orders. We are not taking a dipolar mode ad hoc and making this. I mean, in this plasmonic potential, we are doing an expansion in all the modes. So we are implicitly, but considering all the orders of the electromagnetic possible modes associated to the cavity. So that's no problem.
I see. Thanks.
Okay, Professor, one last question. Hoyle, you may talk.
Oh, hi, Javier. Sorry, I have a question. Can you go back to the electroluminescence story of the tautomers? Yeah, so yes. Can you, a few slides before, you were basically showing that the electroluminescence maps are overlaps between these orbitals of the molecule and some dipolar feature. Can you remind me what is that dipolar feature that you are really talking about?
So what we are doing basically here is to calculate this G factor, right? The coupling strength of this cavity and map it as a function of position of this tip Pico-cavity. And exactly the same way that I map, for example, this one here, the G with the full quantum model of the porphyrin, we do exactly the same that we do here with the porphyrin, we do with the free base. And then instead of a 4 low, what we obtain for the hydrogens along this direction, for the QX1, if you want, is to calculate a map of the coupling strength. And then we say that the emission is proportional by Fermi-Golden's root to this coupling strength to the square. So basically this pattern of coupling strength gives you the electromagnetic part or the coupling part of the emission. So if there were no influence of the current driving, exciting, or pumping, this would be the pattern, a dipolar pattern, right?
Yes. But you are doing it also, I see. So, but you are doing electroluminescence, that's why you need to overlap it with.
Exactly. So if I were doing photoluminescence, then I would need to multiply this for an excitation efficiency, which would be the local field to the square.
Mm-hmm.
But the local field is quite homogeneous in a Pico-cavity, and then here this would not be so modified, right? But now, because instead of pumping with light, this is not photoluminescence, but what we are doing is electroluminescence. It's the tunneling electrons what is driven in the pumping part, in the excitation rate. Here in the pumping part, I need to put something that I didn't elaborate, and it's on this Nature Physics paper, is something that is proportional to the tunneling orbital of the molecule, which is the HOMO to the square, the HOMO orbital to the square. And that's why the product of both is what explains the full pictures. The full picture is a convolution of the electromagnetic dipolar emission and the pumping part through the HOMO orbital. And the product of these two is giving me this substructured dipolar pattern, which is what they find in the experiment. It's very challenging to interpret, actually.
I see. And just very, very quickly, you are basically talking about the interconversion between the tautomers. Have they lowered the temperature enough to actually, say, slow down this interconversion?
Yes, yeah, I don't think they did experiments on temperature. I don't recall. They did experiments though on modifying the bias and see how there was and the current, and then they saw how the switching rate, this millisecond thing was a function of the current. Actually,
I see.
That's the kind of thing they did here in this graph.
That makes sense because there are dipoles that couple to the current, I guess, or something.
If somebody wants to know more details, this is a very recent paper that we published with Guillaume with all the details, the technical experimental details, which of course are the expertise of his team, right?
Okay. Thank you very much.
Okay, we are very sorry that we don't have enough time to answer more questions. And for the next week, we will have Dr. Rodriguez as our speaker, but the title hasn't been finalized yet. And another thing is, for our next postdoc spotlight, we just received a message that for experimental section, it's Q Yang Park from Princeton University is will be host a talk, will have the talking in the next postdoc spotlight. For the theoretical part is Claudia Clement from Universidad Autonomia de Madrid. And for those whose question wasn't being answered, you can keep your question in Q&A. We will send to a professor later. And let's thank Professor Javier again for this wonderful talk, which enables so many interesting discussions. And this would be the end of this webinar, and hope to see you all next week. Bye-bye.